morning, everybody, and welcome to the 184th meeting of the Acoustical Society of America, coming to you from Chicago. My name is Ashley Piccone, and I am the press officer at the American Institute of Physics. We have some great presentations today, starting with a press conference of 4 presenters this morning and more throughout the day. So videos of this live stream will be available upon request, and we're happy to connect anyone with the presenters. Just email media@aip.org. After we hear from each presenter, we'll have some time for questions, so if you're online, feel free to type those into the question box. So let's get started. Our first presenter is Seonyeong Park from the University of Illinois Urbana-Champaign, and she's going to describe how skin color can impact breast cancer screening methods. So, Seonyeong.
Thank you for the kind introduction, Ashley. Good morning, everyone. I'm Seonyeong Park from University of Illinois Urbana-Champaign. My talk is about virtual imaging trials to investigate the skin color, impact of skin color on three-dimensional optoacoustic tomography of the breast. First, let me talk about the motivation behind our work. Many studies have reported racial bias in technique that employs tissue optics. One of the examples is pulse oximetry. A study has shown that pulse oximetry can be 2.5 times less accurate in patients with darker skin, which may have contributed to increased mortality reported in Black patients during the COVID-19 pandemic. Since optoacoustic tomography, OAT, is also based on tissue optics, we wanted to find out whether racial bias exists in OAT imaging as well. So what is OAT? It is a biometrical imaging technique that combines the principles of optical imaging and acoustic imaging. In OAT, a short laser pulse at a near-infrared wavelength is used to illuminate the object, in our case, a breast, causing it to absorb the optical energy and create acoustic pressure waves. Then these pressure waves are measured by ultrasonic transducers. With those, we can reconstruct an OAT image as shown in this video. This is a clinical 3D OAT breast image. The data was acquired by Tomoe Laboratories. As you can see, the blood vessels are easily visible in the OAT image. This is because in the near-infrared wavelength range, hemoglobin absorbs more light than most other molecules. So breast imaging is one of the promising applications of OAT due to its capability to assess tumor angiogenesis and hypoxia, non-ionizing radiation, high optical contrast, and relatively high spatial resolution compared to purely optical imaging. So many 3D OAT imaging systems have been proposed, each with their own unique designs. However, we don't really know how skin affects the system's ability to detect breast lesions. To figure this out, we need to do comprehensive human subject studies, which can be expensive, time-consuming, and pose ethical concerns. So we had to come up with a different approach. Let's think about building a spaceship. NASA doesn't just dive in and start building it because that would be insanely expensive and potentially dangerous. Instead, they use virtual simulations to test and refine the design first. Similarly, we established a framework for virtual imaging trials. These frameworks generate the numerical breast phantoms, digital breast, and simulate OAT image formation. This figure on the bottom right presents an oxygen saturation map within the breast, created our framework. Using this framework, we conducted lesion detectability tasks by assuming exact knowledge of breast tissue and lesion. Although this is an idealized scenario, it provides valuable insights into the influence of skin color on 3D breast OAT images. As shown in the bottom left figure, we compare the two images that mimic existing systems across different skin colors. So here is our study design for the investigation. First, we created numerical breast phantom that represent healthy and unhealthy breast, we consider 6 different lesion locations and 5 skin colors, which were selected from within a realistic range. Next, we simulated OAT image formation, assuming simple measurement noise. This slide shows virtual imaging of imager A design. Then, according to signal detection theory, we calculated a lesion detectability measure from the simulated acoustic measurements. Specifically, this measure was the area under the receiver operating characteristic curve, AUC. We conducted the entire procedure for 2 imagers, 6 lesion locations, and 5 skin colors. Now, let's take a look at the key findings from our study. For lesion located along the z-axis and or at a depth of 10 millimeter, the shallow depth, which correspond to lesion location 1, 4, 5, and 6, both imagers showed relatively high and comparable performance in signal detection tasks, regardless of skin color. However, for lesion locations 2 and 3 with the red fonts, detectability was lower, especially with the imager B, which does not illuminate the breast from the side. Therefore, here we focused on the results for the lesion locations 2 and 3. The plot in this slide showed the relative AUC improvement by imager A for the lesion locations 2 and 3. So compared to the imager B, imager A improved lesion detectability by up to 4.8% in the lightest skin and up to 7% in the darkest skin. So lesion detectability in darker skin was more affected by imaging system design than in lighter skin. To improve lesion detectability in darker skin, the laser power to acoustic noise ratio should be increased. To summarize, we found that in individuals with darker skin, lesion detectability can vary depending on the design of the OAT imaging system and lesion location. Therefore, to ensure reliable breast cancer screening for all patients, we recommend that future OAT imager designs consider the impact of skin color on lesion detectability. Our framework can be a useful tool for optimizing system designs in the early stages of technology development. In our future work, we plan to conduct more realistic lesion detection tasks, and also we plan to investigate the impact of skin color on tumor hypoxia detection using 2 wavelengths OAT data. Finally, I would like to thank Dr. Anastasio, Dr. Villa, and all our lab members. I'm happy to answer any question. Thank you.
Great. Well, thank you, Seonyeong. So I'll start us off with a question. I'm curious, can you just tell us a little bit more about what advantages OAT has as a technique compared to other breast cancer diagnosis methods?
So current gold standard is mammography, and then it involves in ionizing radiation, so it's not that safe. And also it squeezes the breast when scanning. So OAT does not need that much compression, and also it is free from ionizing radiation. Also it's cost effective compared to MRI because MRI is really expensive. And also during the scanning, it's really loud. Yeah, and also ultrasound and the MRI, those and also mammography, those are kind of like hard. I mean, the lesion can be hard to detect for the dense breast, usually for the young woman. So OAT, because it uses angiogenesis and hypoxia of tumors, so it has like different feature. Yeah.
Okay, great. Do we have some questions from the audience? Or not the audience, the live streamed audience?
Yes, we do. So we have a question from Maura Shapiro at AIP, and the question is, to increase the detectability in dark skin, you suggest increasing the laser power. Are there any negatives to increased power?
Yes, there is. So there is a limit. For the safety, there is a maximum permissible exposure for skin. So we cannot increase the power up to certain range. So for example, like 20 millijoule per centimeter square. But what other thing we can do is reduce the acoustic measurement noise, because I said increase laser power to acoustic noise ratio, right? So we can reduce the acoustic noise. Mm-hmm.
And thank you so much. And we do have one more question. This is from Avery Thompson. Is this data being considered by device manufacturers? And are they taking action to improve their designs and implementations to account for skin color?
Could you repeat again?
Sure. Yeah. The question is this data being considered by device manufacturers? And are they taking action to improve their designs and implementations to account for skin color?
Okay. So other modality, you cannot really choose different variety of design, but because this is OET, so its feature is we can consider the engineering limitation, and then like depending on how we design, the image quality can be different. So as far as I know, people are actively working on designing new imaging systems, but not many group investigated on the skin color yet. So that's why, like in my talk, my conclusion is we should consider skin color when designing the new system.
Awesome. Well, thank you, Seonyeong. And we'll be back in one moment with our next presenter. Oh, we have one more. Just kidding. One more question.
Sorry about that. You had said reduce acoustic noise. How do you reduce the acoustic noise? Is it like in your signal processing after you have the data, or is it in the room itself there's something that's noisy?
So the transducer has the specific noise level, right? So if we hope that a transducer can be improved a lot hardware-wise, then it can be reduced. And also the other thing is when we scan, not only a few scan, we do the multiple scan and then average it, then maybe we can reduce some acoustic noise. But then the downside of it is it increases the scanning time, and also it may introduce the motion artifacts.
Okay, now we'll be back in one moment with our next presenter. So thank you, Seonyeong.
Thank you.